All right, so remember this problem, they give us, and I was just explaining this to Maddie, and I'll say it again. This time they give us product concentration initially. They don't give us anything for reactants, so these are 0. This is a hard concept for students to understand because, you know, this is the second year you're taking chemistry, so first Regents, now AP, you're basically conditioned to say reactants form products. Well, in this one, there are no reactants initially, there's only products, and if it's equilibrium, we're going back and forth, you can definitely form reactants starting with products. There is reactants and products, but in a reversible, you can almost, you know, interchange that term. So this 0.04 is going to decrease, and these two are going to increase. So that's why in your change row here, these two are going to be plus x, because you can't get less than 0, right? So you're just increasing. And then this one, you're subtracting 2x. Why? Because there's a 2 in front of HI. Yep. That's the key, and now make sure you write this down correctly. These are x, and then this you have to combine, 0.04 minus 2x. That's, the whole ICE table is the key here to success. I'm not worried about the math. You guys can do that. I know you can. You just got to set it up right. So now the only other tricky part, remember, look up here, this entire equation is squared, right? Because it's HI. This is all of HI in one parentheses squared. So it's going to be 54.3 equals 0.04 minus 2x. The whole thing is squared because this whole thing is the concentration of HI over x times x, which is x squared. So it's x times x. I'm just going to combine that. So this works out nice. We take the square root of both sides, and we end up getting 7.369 is what I get here. So let me just rewrite that. 7.369 equals 0.04 minus 2x over x. Cross multiply, we get 7.369x equals 0.04 minus 2x. This is easy now, right? So we add 2x to this, then divide by that number to get x by itself, and we get 0.00427. So that's what x equals. Questions? So final answer, these two, that is the answer. That is the concentration of H2 and I2 at equilibrium. Now we have to plug this in for x, multiply 2 times that number, subtract from 0.04, and we get 0.0 what? Yeah, so this would become 0.0314. Yeah. All right, and then those two would be 0.00427. So it only changed a little bit. Why? Hold on, Dylan. Why is that such a small change? It only changed by less than 100th, which is not very much. Why would we expect in this problem for the products to not decrease a lot at equilibrium compared to initial? This could be like a second part on the AP test. So you have to do all this business, you get your answers, then it might say, explain why that change is so small, you know, or justify your answer, something to that effect. That's a small change, justify, you know, your answer. Why is that a small change? Why? Something you learned before. Look at K. Is that a big K or small? Big. Anything above like 1 is big. Anything above 10 is really big. What does that mean? There's a lot of products, right? P over R, product over reactants. So it's going to make sense that at equilibrium, if this number is pretty big, you're not going to lose a lot of concentration. So this number shouldn't be a lot smaller than what we started, because if it was, that would mean K was small and we're forming a lot of reactants. That's a tiny amount, 0.0043. That's a tiny amount of reactants. That makes sense. We should have more products than reactants because 54 is a big number. That's the kind of stuff that, when I get 4s and 5s, you got to get that right. Maybe you can do the math, but you got to be able to get those why questions right. All right? Okay, question, Dylan.
Never mind.
You sure?
Yeah.
All right. Okay. Moving on. Let's see here. I don't think I want to do this one with you. No, we'll do it. Okay. All right, so we got, how many problems did we just do? 2? Right? 1, 2. All right, this is 3. All right. We're just going to do all of these practice problems that I plan on doing because then that's it. I'm not going to kind of do this again in class. We'll use the homework to hopefully fix up any issues we have. Here we go. All right, so I'm just going to read this one. I'll write down the reaction. I'm going to read out the details. At 800 degrees Celsius, the value of Kc is 48.7. So Kc, 48.7. And we're going to do a Kp, one with pressure here in a minute. But so we got a K value of 48.7. We have 0.25 moles of HF. So we're going to kind of base on the same reaction we did in our notes, the first problem. We have 0.25 moles of HF. 0.25 moles of HF. We have 0.1 moles of H2 and 0.2 moles of F2. All right, they're placed in a 1 liter flask, so that is your molarity, right? It's placed in a 1 liter flask, so those basically might as well be molarity numbers, and allowed to reach equilibrium. So these are put in the flask. They're allowed to reach equilibrium. They give you the constant, the equilibrium constant. Determine whether the equilibrium concentration of HF is greater than, equal to, or less than the initial concentration of HF. Explain your answer. So this is what you're given. Here's your reaction. I'll actually write that last part. We're going to determine if the HF concentration is greater than, or greater, less, or equal, oh crap, if the equilibrium, I'm sorry, forgot that. If the equilibrium concentration of HF is greater than, less than, or equal to the initial concentration of HF. So you know the K value. You know the molarity of each part there, H2, F2, and HF. The question is a little different. It's not like ones we just did. They want to know, are you going to have more than 0.25, less than 0.25, or is it going to be the same amount, equal to 0.25 at equilibrium? Because that's what we're starting with. You have to relate that. So I'm going to erase the question, so I have space here. So I want to know, is the concentration of HF greater than, less than, or equal to the initial, which is 0.25? So I'm going to give you one more hint, then I'm going to stop and give you some time. These numbers are initial values. We don't know the equilibrium values, but we really don't need to know them. So you just need to know the initial. I suppose you could actually solve for them, but you don't have to. You don't actually have to solve for equilibrium concentrations to figure this one out. You could do that. What's the initial concentrations tell us, Earl? Q, right. If you guys find what Q is and relate it to K, you'll know which direction this thing shifts, and then you can figure out, are we shifting left or right, and then you'll figure out if it's going to be more or less than 0.25. So solve for Q. Solve for Q. You could actually set up your ice table and solve for the equilibrium concentrations of each one, but you don't need to. That's too much work. Actually, you know what? If you wanted to solve for if you wanted to set up an ice table and solve for x, you would have to use quadratic equations. So let's not do that. I'll show you real quick why that would be kind of a pain. Let's solve for q first. You guys get a number yet? Anybody? Yeah.
Ahead 3.125.
Yeah, 3.125. So it's 0.25 squared over 0.1 times 0.2, right? And that's what, 3.125?
Yeah.
Okay. So Q is smaller than K. So initially, that means we have more reactants than we do at the end, right? Remember, let's think about where this comes from. Products minus reactants. So whatever the K value is, I mean, we know that, sorry, we know the 448.7, but this number here must increase, and this number must decrease, because K is bigger than Q. So this reaction must progress towards the right, towards the products, to reach equilibrium. Essentially, another way to explain it, I didn't say this the other day, how do you go from 3 to 48? How would you do that? You'd have to give more products. You have to basically increase that number, so you're shifting right, making this bigger. I don't think I worded it that way before. So anyways, we're shifting right, we're going to make more products. So if you start with 0.25, you're definitely going to end up with more. So the answer is it's going to increase, greater than 0.25. If you wanted to set up the equilibrium expression, it would look like this, right? Just to review again how to do this, it would be 0.1, 0.2, 0.25. What would the change be? Minus x, plus 2x. What would this be? 0.1 minus x, 0.2 minus x, 0.25 minus 2x. How would we set up the k value, the expression here? Oh, sorry, we had it. Keep forgetting we have it. It would be 48.7 equals, what would go on top? 0.25 minus 2x squared. Right? Here's your product, 0.25 minus 2x. What's that? Oh, I'm sorry. Plus 2x. Yep, my fault. Plus 2x. And then what would the bottom be? 0.1 minus x times 0.2 minus x. This is a problem, right? You can't just combine those and square it. We could do it. I don't want to do it. So, but you could. You literally could do this. All right, you're capable of doing it. And if you solve for x, you would see this number would be bigger than 0.25. But the concept is the Q versus K. All right, another problem. Let's do, okay, we'll do this one first, then we'll do this one, and then I'll give you your homework. All right. So what I'm trying to do here is go through every single possible type of problem, like just the generic example. There's obviously like hundreds of problems you could do. But the first one we did, what did we solve for? The very first problem, what did we do?
Solve for the product. Final concentrations.
We solved for equilibrium concentration for the first one. What did we do in the second problem in the book? Same thing, but the reaction was flipped, right? So it was just a different direction. This one, we use Q and K. Okay, so now what's the only thing left to do? So the first two we solve for equilibrium concentrations. This one we use K and Q. That's the only thing left to do with these.
Solve for K.
Right, solve for K. Okay. All right. Sulfur trioxide decomposes at high temperatures in a sealed container. What would that reaction look like? Use your chemical intuition. Sulfur trioxide, what's the formula? SO3. Sulfur trioxide decomposes. What do you think it decomposes into? I'll give you a hint. You could breathe one of the gases. O2, very good.
And,
Did you say O2, Ben?
I did say O2.
What's the other one?
Ben, did you say O2?
S.
I did
O2.
say O2.
Is it balanced?
It's negative. I wonder if Ben said O2.
What do I need? 2 and 2. Okay, there's your reaction. Now, initially, the vessel is charged at 1000 Kelvin with SO3 at a partial pressure of 0.500 atm. So initially, charge just means it's filled with 0.500 mole, or no, not moles, atm of SO3. So that's initially what's shot into the flask, the vessel, sorry. At equilibrium, SO3's partial pressure is 0.2 atm. So at equilibrium, it's 0.200 atm for SO3. Calculate the value of Kp. So calculate Kp. So again, sulfur, this was how the problem would be worded if I read it all at once here. Sulfur trioxide decomposes at high temp in a sealed container. There's the reaction. Initially, the vessel is charged at 1000 Kelvin with SO3 at a partial pressure of 0.500 atm. At equilibrium, SO3's partial pressure is 0.200 atm. Calculate the value of Kp at 1000 K. So I'm going to let you try and figure this one out. Use what you just learned. Solve for K. So obviously, I'm going to say one more thing. I talk too much sometimes. Obviously, there's not going to be a variable here except for K. You can't have a minus X plus X, and you won't be able to solve for K. So when you set up your equilibrium expression, you're using numbers to solve for K. K is the X. I gave you initial, I gave you equilibrium. Lead a horse to water, Dylan. Finish it, Dylan.
He's calling us good. No, he's calling us. What is it called?
Can't make you drink. Thanks.
Is that it?
So I led you to the water.
What was that called? What were you doing, babe? What was Dylan's Stella's name? Midnight. Midnight. Dylan's name is Yeah, we get the Caesars and then you don't have a strong constitution. Yeah,
Set up your ice table. Set up your ice table. You're on the right track. There you go. Where can we put that 0.500? That's really funny. The giant finger. Hopefully Mark's secure gets a kick out after watch that.
What?
Stuck my finger in front of the camera and said giant finger in weird voice. Well, because I moved the camera, man. I didn't need for it to happen. I just didn't fast. Initially, equilibrium. I, E. So initially, it's 0.5. At equilibrium, it's 0.2. So you're right. Everything you've done so far, you're good setup. Just got to put the numbers in a different spot.
Basically saying K was X, basically saying we want to find K.
So ICE, ICE. Initial concentration of SO3, or initial partial pressure. Remember, with gases, partial pressure is basically the same thing as concentration. In other words, you can do all the mole ratios, equilibrium, everything. Okay? So, expect either one. 0.500 goes here. Now what? It gives you the equilibrium. Ben, where's that going?
SO3 at E.
Good. So I'm just going to do this because it's a little bit confusing for me. So 0.200 ATM is here. We're solving for K, so they gave you enough information here. How do all reactions react? Depends on their mole ratio, right? Well, pressure works the same way. So if this is decreasing to 0.2, what's the change? Minus 0.3, very good. Now, you do know how to do this because you just did other problems except instead of using X, we're using 0.3 now. That's why they give you the 2 so you can figure out X. Initially, these are going to be 0. But now it gets a little tricky. Is that 0.3 or is that 0.6? Or is it 0.15? What's the ratio between these two? Is it 1 to 1?
Yeah.
So if this is 0.3, this has to be plus 0.3. But kids in the past will make that mistake. They'll say, no, no, there's a 2. Yeah. There's a 2 here too. Okay? So just keep that in mind. Now what about O2? 0.15. 0.150. Now, since this was 0, the change is the equilibrium, 0.300, 0.150. Now you guys can solve for K. So you really got to pay attention to the coefficients to do all these ice tables. Yeah, don't forget to square the squares, the ones that get squared, and
I got that, but different. Lined up like hundreds over.
0.3 squared times 0.15 divided by 0.2 squared. Don't forget 2 here.
I switched it around.
Products over reactants. It's 0.338. 0.338. 0.338, which makes sense because your products, right? Depending on, smaller than reactants if you're squaring that. 0.338. We got one more to do. I know this was a tough 2 periods. It's all the same thing, just tweaked a little different, 5 different ways. All right. Now, one more practice problem, then I'll give you the homework. This is working out nicely. Tomorrow we'll talk about KSP. No, we won't. You got a quiz tomorrow. All right, here we go. This was gonna be on your midterm. I wanted it to be on your midterm, but you didn't know how to do this yet, so I took it off.
Thank you.
So, well, that would have been just stupid, I feel like. So here's the, given the following. Here we go. You have COCl2.
Yeah, I was kind of a little bit upset that there's no empirical formula stuff on that.
Yes, there was. There was 2 questions on that.
Oh, was there?
Yes.
Well, obviously.
2 multiple choice questions.
I meant the short answer.
Oh yeah. Well, that was too easy.
Come on. I mean,
maybe it'll be on the real test. That would be wonderful.
Only 2 people got 100.
Here we go.
Quiz and Pat,
If the initial pressure in the flask, so you're given that reaction, is 2.0 ATM. So this reaction is taking place in a flask. I always leave out a little bit because I don't feel like writing all the details, but it's in a flask. It's at 700 K. Remember, they have to make sure the temperature's constant, otherwise the K isn't valid. So